Hello, and welcome to this webinar, Rethinking Probiotic Stability, New Solutions to Old Challenges. This event brought to you by Packaging Strategies is sponsored by Aptar. I'm your moderator, Derek Teal. Thanks for joining us. Today's presenters are Billy Abrams, Senior Vice President, Business Development at Aptar CSP Technologies, and Dr. Gregory Zayer, Chief Scientific Officer, UAS Labs. Billy has worked at Aptar CSP Technologies for 23 years. He started in operations, transitioned to project management, and has been responsible for business development for more than 15 years. Billy has a BA in economics from Cornell University and an MBA from the Johnson School of Management at Cornell. Greg has dedicated his professional career to probiotic advancement, making him not only a critical component of UAS Labs, but a world-renowned expert, educator, and speaker in the field. A graduate of the University of Wisconsin-Madison, Greg received his MS and PhD in food microbiology and toxicology, studying the pathogenesis of various organisms, including Clostridium botulinum and Salmonella typhimurium. Don't forget to submit your questions, and later in the programs, our presenters will address as many as possible. Today's event is being recorded and archived on www.packagingstrategies.com. And now I'm excited to turn it over to today's first presenter, Billy Abrams. Billy?
Great. Well, thank you very much. I appreciate the introduction. Thank you, everybody, for joining today. I'm Billy Abrams, responsible for business development for CSP. So first, let me give you a brief introduction to the Aptar Group. So Aptar's been around for about 70 years, has manufacturing facilities throughout the globe, and is really focused on three divisions: pharma, beauty and home, and food and beverage. CSP was acquired by Aptar about 2 years ago or so. And CSP is really a material science company. We've created unique active polymer technology that's used throughout a range of industries, primarily in the medical industry, and that enables us to provide active packaging solutions. We have manufacturing facilities in the United States and in Europe. And this is mature technology. We manufacture over billions of products over the life of our company. We manufacture hundreds of millions of containers and components every year, with a large focus focused on our intellectual property. What we're going to focus on today is our three-phase active polymer technology, which is what enables us to provide superior protection for probiotic products and other moisture-sensitive products. So, what exactly is our three-phase active polymer? So first of all, I think it's important to recognize this is a platform technology that can be applied across multiple product delivery platforms. But in its essence, the active polymer is typically a three-component blend. The first ingredient is the major phase polymer, whose primary role is to provide structure. So it's a typical polymer. Polypropylene, polyethylene are the ones we most commonly use. The second ingredient in the blend is the guy that has to do the work. So in these applications, it's always a particle, and in this application, where we're focused on absorbing moisture, that desiccant, that particulate is a desiccant particle. The third ingredient in the blend is what enables this to work, and it's another polymer that's immiscible with the major phase polymer, meaning that when you put polymer A and polymer B together, you don't end up with an alloy of polymers of that resulting polymer. What you get is a network of polymer B within polymer A. And that's very important to understand, because most of your structural polymers, polypropylene, polyethylene, they're hydrophobic. They're moisture barriers. They want to keep moisture out. Well, when moisture is within the confined headspace of a package, we want that moisture vapor to migrate into our active polymer matrix. And so the role that the channel plays is the channel is hydrophilic. And what happens during the extrusion process is that hydrophilic polymer coats and distributes the active particle throughout the cross-section of the blend. And the resulting morphology, which you can see on this slide, what we end up with is a very unique morphology. We end up with a network of interconnecting hydrophilic channels, and within the channels reside the moisture-absorbing technology, in this instance, a desiccant particle, and that's located throughout what is typically a hydrophobic structure. So we create a network of hydrophilic pipes, if you will. Within those pipes are the active particles so that they are able to absorb the moisture vapor from the headspace for moisture that is latent, moisture that could be residual with the product, or moisture that can ingress into the package over time. And because those channels are located throughout the cross-section, and because the particles are distributed throughout that cross-section and throughout that channel matrix, we get full utilization of the actives throughout the entire cross-section. It's not simply a surface absorption phenomena. We get absorption of moisture vapor throughout the entire cross-section of the active polymer wall. So the active particles can be engineered and selected to absorb gases, be it moisture, odors, oxygen, volatile organic compounds like formaldehyde, basically things that are in a gaseous phase. And we can select chemistries to neutralize them. Typically, we're looking at absorbing gases, but there are applications where we also can use this technology to release gases, like antimicrobial agents, for instance, or even aromas. So that basic morphology is what really enables our technology to be effective. So here's just some basic charts that really speaks to what the channeling enables us to do. Desiccant in and of itself is very well characterized with respect to how much moisture it absorbs, and the moisture absorption is a function of the mass of the active. So in the chart on the left, these are all active polymer formulations with the same mass of the active ingredient. And what we're able to do is manipulate the kinetics of absorption. So we can't make desiccant absorb faster than it would in nature, but we can slow it down, which has some benefits when one looks at controlling the capacity and absorption during processing, let's say, or during exposure time in a packaging environment. So we have applications, for instance, in the medical field for medical devices where they have a very, very long assembly time, yet they still need to be protected from moisture during their shelf life. And so using traditional desiccants, the desiccants would lose their capacity over these very long assembly times, but because of our nature of being able to control the kinetics of absorption, we're able to slow it down so that these products don't lose their capacity in a traditional packaging environment. And so the chart on the left depicts 4 different active polymer formulations, the uptake curve. All of those formulations will ultimately yield the same absorption capacity, but that graph illustrates the degree to which we can control the kinetics of absorption. Likewise, we've also done a lot of work with oxygen scavenging, and the graph on the right portrays the oxygen concentration in the headspace with respect to time. And you can see that the technology is very well characterized with respect to O2 pull down as well, basically based on how much oxygen is available. The more oxygen absorbing capacity you provide, the steeper the pull down. So if somebody said to CSP, hey, can you absorb 20 cc's of oxygen, and we provide a solution that absorbs 20 cc's of oxygen, that would have a ratio of 1, what I would call a power ratio. And you can see the O2 pull down with respect to time. If somebody says, geez, we'd really like to see if we could accelerate and pull it down faster, then we said, well, geez, instead of having to absorb 20 cc's, what if we made a solution that could absorb, let's say, 80 cc's? Well, then that's the blue line on that chart where you can see that the O2 pull down is that much faster. I think the general takeaway from those slides is the degree to which We've been working with this active polymer technology now for 20 years or more. And so we really do have a very good understanding of how the technology works and the degree to which it's characterized. I think one thing that's really important for the participants to understand is that in order to enable active packaging, like the use of our active polymer, you have to look at the package as a system. And so when we're putting our chemistries into polymers and trying to create a controlled environment within a package, it's necessary to be using a tightly sealed environment. I always like to say you can't desiccate the world. So if you have a leaky package, and there's a couple of ways packages that could be leaking. You could use a material, for instance, to make the package that has a high moisture vapor transition rate. So you can put a ton of desiccant, let's say, into a paper container, but paper is not a very good barrier to moisture. You're just going to exhaust your scavenging solution. So you can have permeation through the walls of the container, but very importantly, you could also have moisture ingression through seal interfaces. So it's very important to understand and to realize that you need a tightly sealed container if you're going to use an active packaging solution, because the capacity and the kinetics of absorption, they're finite. So you need to be able to characterize the package to understand what the performance will be like with respect to time. So how does that manifest itself? Well, and how we commercialize it? Most commonly, we're known for the CSP vials and bottles that we manufacture. So we make what we call a vial, which is an integrally hinged flip-top container, and those where the inside wall is made of our active polymer, and the outside wall is made of a traditional barrier polymer like polypropylene. We close those vials in the mold. That's a patented technology of ours as well. And because of that tight seal and that closing mechanism, we are able to manage the ingression of moisture such that the active polymer can be effective and can provide protection over the shelf life of the product. What's also unique about the flip top is that it effectively reseals upon opening and closing. So the other way we've commercialized this with rigid containers is to make a bottle that's compatible with a traditional screw cap closure. So we have various sizes that we make, but it uses the same principle. The inside wall is made of the active polymer. The outside wall is made of a barrier material like polypropylene or polyethylene. And what happens, what's really unique about our solution is that we use a two-shot molded approach where the first shot is the active polymer. The mold rotates. That active polymer sleeve is inserted into a cavity where the outside wall is then over molded over the active polymer. And so the product inside is effectively completely surrounded by the active polymer. So moisture that ingresses, for instance, through the outside wall, and even though you're using a barrier polymer like polypropylene or polyethylene, make no mistake, moisture will ingress into that package. Those moisture vapor molecules are, as they permeate through the outside wall, are absorbed by the active polymer liner before they have any opportunity to interact with the product. And that ends up being very, very robust because sometimes, particularly with probiotics, a little bit of moisture can go a long way to initiating the decay mechanism. So, for instance, ultimately, if you're looking, well, what's happening inside of these active polymer containers? Here's a quick snapshot of what's going on with respect to RH over time in two of our containers that are commonly used in the probiotic industry, a 64 ml flip-top vial and a 110 ml flip-top vial. This data is based on storage at zone 2 ICH condition, 25C, 60% RH. This assumes there's no product in the containers. the active polymers do tend to be more aggressive than the products themselves. So adding product we wouldn't think would accelerate the moisture ingress per se. And this is done, these readings are measured when the bottles are the most aggressive as well at the earliest point in their life. But what you can see is that we are maintaining very low levels of relative humidity throughout the entire shelf life and ultimately the use life of these products. Likewise, we have similar profiles of RH maintained with respect to time for the popular bottle SKUs that are used in the industry. We have three primary sizes, a 78 ml, a 112 ml, and a 150 ml. And these charts represent the RH with respect to time at both 25C, 60% RH, which is zone 2 ICH, all the way out to zone 4B, 30C, 75% RH, which is, as many in the industry know, is a very, very stressful condition and a very difficult condition of which to obtain long-term probiotic stability. There are other formats in which we've been able to commercialize our active polymer technology. And one format that is particularly relevant for this industry is the ability to extrude the material into a film, which is not a primary packaging material. You wouldn't make a container or a pouch or something out of the active polymer, but rather you would apply the active polymer to the inside of a high barrier flexible package, like a stick pack or a sachet or a blister pack. So there are standard thicknesses and a range of thicknesses that we can support with this. Again, the absorption capacity is a function of mass of the film and the mass of the active. But one unique thing that's interesting about this material is that it's polymeric in its nature, and the flexible materials into which it's applied also have a polymeric lining, which means that without adhesive, but simply through heat and pressure, we can effectively laminate our material to these foil substrates and not have to introduce adhesives, which can be costly and can off-gas, but our material can be what we call heat staked onto these substrates so that they're integrated seamlessly into these package formats on the packaging line. So it's not like you would open up a stick pack or a sachet, some sort of a sealed pouch containing powders or granules and have some sort of a loose desiccant float out or drop out or into a package. Our material is affixed to the sealing layer of those foil constructions, and that it provides a seamless way of introducing that active polymer scavenging technology into these flexible formats. So specifically, one of the application areas is what we call active blister. And one can envision, there's lots of sources of where moisture and oxygen, be coming from. Can be coming from latent moisture or oxygen trapped within the formed blister. It could ingress over time. And our material, the active polymer, can be applied onto the foil lid stock as the foil is unwinding on a blister line. So it's bespoke automation, a module that would have to be added to either a blister line or stick pack lines or sachet lines. But that is work that we've done and we've commercialized with other customers, with many customers and across industries to use this to enable the use of our active polymer film. And, historically, let's say alu blisters have been considered the gold standard for protecting products. But as many have encountered with probiotics, latent moisture in and of itself can be a culprit. So alu is really potentially not the best solution in this industry. If we can introduce our scavenging technology into the blister, we can reduce the initial water activity level, and we're going to get to that in subsequent slides. So it kind of makes you rethink the way and some assumptions people have typically used in drug development or in probiotic product development and packaging when they would sort of reflexively lean to alu-alu blisters as the gold standard for managing moisture or keeping moisture out. I agree that it does a great job of keeping moisture out, but it does not do an effective job of managing latent moisture. I think the easiest way to think about, well, geez, what benefit can I get of adding the active polymer into a blister configuration is it's very difficult to make a general statement about how we would reduce latent water activity, because that's highly dependent on an individual company's initial drug product or probiotic product. But rather, one can look at, well, based on a blister configuration, based on the, and when I mean a blister configuration, I'm talking about the selection of the barrier film. So in this example, we've modeled Aclar and 3 different versions of Aclar, which is a very commonly used high barrier thermoform material for blisters. And there are others, heavy gauge PVDC, PVC, and other solutions as well. But the ingression rate of moisture is inversely proportional to the amount of the barrier, and directly proportional to the testing condition. So as you crank up the temperature and humidity, you accelerate the moisture ingression rate. So one of the things, I think an easy way to model this is to say, well, based on the ingression rate of moisture into a blister, which we know is impacted by the selection of the forming material and by the environmental condition, we know the absorption capacity that a piece of our film will provide. So we can do a rough calculation to say, if you use a piece of film that is X by Y by Z in dimensions, in this example, about 6.5 millimeters by 13 millimeters by 1 millimeter thick, basically a size that would be compatible to protect a size 0 blister, we could provide days, months, and potentially years of RH protection based on the environmental conditions and the barrier material selected to form the blister. And that's what's presented in this chart. And you can see that that can be very, very powerful with respect to shelf life extension. With that, we're now going to move into the data part of the presentation, and I'm going to hand off to Dr. Layer at UAS Laboratories to talk about some studies that both they've done and some of our other customers have done with different configurations using the active polymer.
Yeah, thanks, Billy. Really great understanding now of the technology behind the active components in your technology. So what I'd like to talk about is some practical applications of the CSP, either the active film or the active vials, and how that affects probiotic stability. Probiotics in the desiccated state, typically freeze-dried state, to maximize that stability, we want to keep it very dry. And in order to do that, which is when we say dry, we speak in terms of water activity, which is a measure of relative humidity in a microclimate or a sub-environment of the packaging material. So the slide we're looking at now is describing the film technology in a blister pack application. And so we're looking at water activity on the y-axis, and we're looking at time on the x-axis. And you can see there's this immediate reduction of water activity in the capsules that are housed in blisters containing this active film. And you can see the dimensions of the active film along the bottom of the graph, where there's a steady state or a slight rise in the water activity of the standard blister material. And as I mentioned earlier, to maximize the viability of the probiotic bacteria or multi-strain mixture, as in this case it's a 12-strain probiotic mixture targeting 10 billion CFUs. To maximize that viability, we want to keep that water activity low. And one common theme that you'll see as we roll through some of these graphs of different delivery vehicles is this rather immediate reduction and then stabilization of water activity when the material is using either the active film or the active vial technology. So if we look at what does this mean in terms of cell count maintenance, you can see here that the blue line above, you see a very different decline kinetic than you do in the material stored in a capsule in a standard blister. So the blisters that had the active film applied to it do a much better job of maintaining probiotic viability than the blisters that are just your standard blister. In this case, we see over a 2x change in viability over the course of 1 year, and that would continue to be amplified as we go out in shelf life. If we look at slightly different technology, but using the same active film pieces, we're talking stick packs. So this would be a powder filled into a stick pack, a foil material that had the active film applied to it. We're comparing two different dimensions of the active film. So same thickness of the material, but an overall length difference, which is going to result in a different overall absorption capacity. And that's pretty apparent even at week 0. So stick packs are made, powder is filled into the stick pack, it's sealed, they're taken off for evaluation for water activity. The blue columns represent the initial water activity determination, and you can see the no active film is at 0.151. The active film with the 17.5 millimeter length is at 0.126, and then the longer active film is at 0.086. So again, even initially, you see this rather immediate effect of absorption capacity and the differences even between the two different material dimensions of the active film. But perhaps most importantly is what happens over time. So after 8 weeks of storage, you can see that there's a slight increase in relative humidity in the the no active film standard stick pack material. This could be due to just relative equilibration within that stick pack. It could be due to maybe some minor micro leaks as well, where you see some ingress of moisture vapor due to the material chosen or perhaps a seal. But you don't see that in the materials, the stick pack materials that had the active film applied to it. And again, you see a magnitude of difference even as you increase the absorption capacity, you see a corresponding decrease in the water activity of the material in that stick pack. So just another example of the benefits of this in a film type application. But again, the question is always, that's great, it reduces water activity, what does it do to culture stability? And you can see this nice progression of stability kinetics, the blue line representing the most absorption capacity, so the largest piece of the active film, the gray line representing the smaller piece of the active film, and then the orange line representing no active film. I should also highlight that the y-axis is depicted in a logarithmic scale. So what we're really seeing is tenfold changes for every log reduction. So this is a quite dramatic change in probiotic stability, which is correlated to that water activity reduction. A unique application of probiotics is in oil drops. You see this especially for infants. And this study, the data provided by GLAC, was looking at using a tablet containing this active polymer that was within this oil matrix containing the probiotic component. And again, we're looking at cell viability in this case at a relatively high temperature of 37 degrees centigrade. So that's not something that we would ever recommend. It's more of an accelerated view of what might happen. So this study goes out roughly 4 months or 16 weeks. And you can see this precipitous drop in viability in the gray line, the control material, whereas you see this relative stabilization of cell viability in the material that had the active polymer tablet applied within it. So again, another demonstration of the benefits on cell viability, which at the end of the day is what we're all most interested in, those of us that are selling probiotics anyway. So if we look at capsules, there's a couple different capsule studies that show the benefits of this. We're still in, we're comparing this to an active alu blister. So we're looking at capsules in a CSP active vial versus capsules in an alu blister that does not contain any of the active film. So just a standard alu blister. And we're looking at two different temperature humidity conditions, 25-60 or 30-65. The top two lines, the orange and the blue, are representing the aloe blister, and you can see the water activity going from roughly 0.11 to roughly 0.17 or so after the course of time. Whereas you see this drop in water activity in the materials, the capsule material stored in the CSP vials. And one common theme is that you see this precipitous drop in the first month, and then you see this stabilization. So there's a relatively immediate drop, and then it's able to withstand any potential moisture ingress into the material and keep that water activity really nice and low. In the probiotic world and the dietary supplement world, we love to see water activities below 0.1. The lower, typically, the better. And here we're at a water activity below 0.05. So what does that mean in terms of probiotic viability? The graph on the left is just representing the 25C 60% relative humidity study, and the graph on the right is the higher temperature and higher humidity. And again, although in probiotic viability studies, many times you'll see these numbers jump around a little bit, what you do see is the blue line is consistently above the gray line. This is representing significant potential cost savings in reducing the amount of overage that you would need to add to a product, because you have this active vial basically acting as an insurance blanket on stability. So again, we see roughly a twofold difference in viability in the materials that are stored in an active vial, active desiccation vial versus an aloe blister. If we look at another capsule study, this is comparing capsules stored in the active vial, the CSP active vial, versus storing it in an amber glass bottle with desiccant. This would be a standard 1 gram silica desiccant in the amber glass vial. You see again, the top two lines are representing the amber glass bottle, and the water activity remains relatively constant with a slight increase from 0.14 up to roughly 0.18 or 9. And again, you see this very typical immediate reduction of water activity in the active vial after the first 1 month, and then the stabilization of around 0.05. So really nice maintenance of low water activities, which in tune results in better probiotic stability. Now, this is an example, as well as the previous graph, of probiotic capsules that are also mixed with botanical materials, in this case cranberry. And many times botanical materials will bring in more moisture, and this is true with any other non-standard excipient. You really need to pay attention to the materials that are chosen in your finished probiotic blend to reduce the amount of water activity coming into the initial formulation. In some cases, it's hard to control that. Botanicals might be one example. So in the case of probiotics and cranberry, we saw on the previous graph this relative reduction and maintenance of low water activities. And here you see again roughly a twofold benefit in terms of cell count. At least going out 18 months under the temperatures, the two different temperatures studied here, one being ambient relative humidity at 25C and the other being 25C at 60% relative humidity. So across many delivery vehicles, from active film being applied to blister packs, to stick packs, to capsules stored in a variety of containers as it's compared to the CSP technology, you're seeing this overall trend of better stability, which is because of the lower water activity and the ability of this active polymer to sequester any moisture that's in the system, as well as prevent any ingressing moisture to interact with capsule material that's containing your probiotic. So with that brief overview of some of the benefits in terms of probiotic viability, I'll turn it back over to Billy to speak a little bit about testimonials related to probiotic benefits.
Great. Thank you very much, Greg. I appreciate that. And thank you for your review of the data. In wrap-up mode here, all we can speak to is really what comes out of the data and what we've heard from our customers globally. So from a range of factors areas where we support, that, if we think about enabling new formulations, maybe as Greg indicated when we're adding in whether it's lactic acid, or these botanical extracts that introduce their own water activity. This technology can really be enabling. As the trends continue to go with claims of higher potencies, and as the geographic region expands for these products, beyond North America and Europe into Asia and Southeast Asia and Latin America and the Middle East, these more stressful conditions, environmental conditions, going from zone 2 to zone 4 and even zone 4B, ICH stability conditions, there's real value now in being able to introduce this type of technology, including the opportunity, when you look at the overall value proposition, to reduce the amount of overage that's going into the product. That's a common approach in the industry to enable companies to meet shelf life claims. As the products become more potent and more expensive, there is a tangible opportunity here to look at backing off on overage as a way to meet shelf life claims, and to use packaging technology to get to the same end game. And so some other areas where customers have told us is that as the increase in direct-to-consumer sales through online shopping, and where our customers lose control, if you will, of how the products are handled in the distribution chain, the active polymer technology provides, risk mitigation to help ensure that the product arrives to the consumer intact and hasn't been compromised because of excursions and because of products stored or transported out of the control of the manufacturer or of the brand. And it's really been enabling these new formulations in terms of ingredients. And lastly, in many instances, we've enabled brands and products that have historically always been refrigerated in the cooler to come out of that shelf consideration and to be shelf stable without all of the costs of having to maintain temperature control throughout the distribution and at the point of sale. So these are just some of the feedback we've gotten from our customers. We believe that these benefits extend to others who aren't using active polymer technology yet to protect their probiotics. And we hope this webinar has been helpful and instructive to the participants. And so we thank you for attending. And Derek, I guess we'll toss it back to you to see if there's any questions.
Awesome. Thank you, Billy. And thank you both for a great presentation. And we're going to start the question and answer portion of the program in a bit here. But before we get to that part, I wanted to ask everybody in the audience to remind you that we'd love your feedback on this webinar. You can provide that feedback to us with our webinar survey, and we use that to improve our programs. And so now, gentlemen, if you're ready to take some questions. So the first one I'll we'll get this to Billy first. Is there a performance difference between the CSP bottles and the CSP flip top vials?
With respect to, I would say in general, not so much. With respect to shelf life, they would be very, very, very similar. There could be a differential in use life, and when the consumer starts interacting with the product. The bottle's moisture ingression is protected by the virtue of the use of an induction seal. And so when you remove the induction seal and you recap the container, there is an opportunity to increase not only the mean value of moisture ingress, but the variation associated with how much moisture enters over time due to repeated openings and closings. Whereas with the flip top, we don't really see any differential between ingression between storage and use. So I would say that would be the differential, the main differential. For shelf life and in meeting label claims, I think both are perfectly valid and robust.
All right, thanks. And so, Greg, to your portion, is water the only threat to probiotic products? This gentleman asked, what about oxygen?
Good question. In my experience, the number one factor is water activity. If you can control water activity and keep that low, the big two factors would be water activity and temperature. If you can keep the water activity low, you're able to withstand more temperature abuse. As it relates to oxygen, unless you're talking about really, truly, strictly anaerobic bacteria, I think that has a distant third in terms of the relative areas of importance on maintaining probiotic stability. It certainly wouldn't hurt to do nitrogen fills and things like that, but it's the order of magnitude of benefit is going to be much greater in the areas of any mitigation you can do to reduce water activity throughout the manufacturing and shelf life process.
And Billy, can the active polymers be added to an HDP for dairy packaging to control oxygen in the headspace?
I'm sorry, for dairy packaging. Okay. Potentially. And again, I think we have to look at it as a system. So when somebody's saying dairy packaging, I'm thinking milk here. One would have to look at the package construction to see how would the active polymer be incorporated into that package format. So for instance, we have a material that oxygen absorbing material that's in a flexible film format that could be applied, into flexible formats or onto potentially the underside of an induction seal. So I think that in general, the answer is yes. But I think one has to look at the package configuration to figure out really how one would integrate the active polymer into that solution. So I say yes, but with a caveat that I've got to see the package and see, and then one to the point we discussed during the webinar, that we need to make sure that the package in and of itself is engineered to mitigate the rate of O2 ingression. So I would hesitate to add any type of oxygen scavenging technology into the package unless the package in and of itself was robust at keeping oxygen out.
All right. And Billy, this one's for you as well. Mark asks, we produce probiotics for animals in paste form for oral application. Do any of the dial-a-dose syringe suppliers use your technology?
Today, I don't believe so. We can as we indicated in the webinar, we can injection mold containers out of this technology. We can also injection mold components. So if somebody has a drug delivery device, like a syringe, for instance, I think that's the way you said this product was administered. We could look at that configuration and determine whether or not, how would one introduce the active polymer into that delivery system. We could potentially make a component of the syringe out of the active polymer, or we would look at the packaging into which this syringe is placed to determine how to incorporate the active polymer into the potentially into the secondary package. So I think the quick answer is yes, it can be done. The second answer is I don't know if it's being done today. And the third is we would have to look at the overall primary package along with the secondary packaging to determine what's the best way or what options we have to introduce the active polymer into that configuration.
Awesome, thank you. And Greg, have you done any work with spore probiotics, and do you have any data that you can share on that, or do you have any resource options where people can go to look up more information on it?
With regards to spore probiotics, was that the question?
Correct.
Yep. Sure. Yeah, we do various application studies in spores. We provide a particular strain of Bacillus coagulans to the market. The advantage of spores is really a stability advantage, and so you don't have the same concerns with relative humidity because of the spore coat that gives them tremendous stability as compared to the more fragile traditional probiotics being Lactobacillus, Bifidobacterium species, etc. So with spores, you have an inherent coating that provides protection from moisture, and so you don't need to take as much care. It allows the spores to be put into delivery vehicles where you wouldn't really consider in some cases, especially in food and beverages. you wouldn't consider the traditional probiotic bacteria. And if there's interest in spores, I would just recommend that they reach out to uaslabs.com and inquire there, and they can get more information on our offering.
Thanks. And so for the active film used in the stick packs, can you tell me what the WVTR is?
Well, let's not think that WVTR is a term that is directly relates to the primary packaging material, right? So, and I would say that's only part of the equation, and that's not germane to active film specifically itself, right? So if you're looking at the water vapor transmission rate of a stick pack material, I don't have that data. That's completely, subject to the brands or the CMOs that are selecting the stick pack material. One would assume that it's a metallized material or some sort of foil coating to minimize the MVTR into the stick pack. And the other thing to consider, of course, which could be more impactful, is the integrity of the sealing. So we've done a lot of work with our customers to characterize the moisture ingression rate, the overall moisture ingression rate, which I would argue is much more relevant than just looking at the WVTR or MVTR of the primary materials. And to quantify how much is actually coming in, it's a function of both transmission and what comes through the seal. But so I don't have a direct answer for you for what is the WVTR of stick pack material. In general, the WVTR has to be very low in order to minimize the rate at which moisture vapor can permeate through. And, and WVTR, just to answer the question to make sure I didn't misinterpret it, WVTR is not a relevant metric for the active polymer itself. We're not a barrier material, so we don't quantify things like MVTR through our material. It's not a relevant metric.
Fair enough. And so, can the active polymers be used in blow molding? Yeah.
Well, I would say not in traditional blow molding, but we can do it through a multi-layer extrusion blow molding process. So we've done a lot of development work with that process, with that manufacturing process. We've actually completed the development in that area and are awaiting an opportunity, let's say, to industrialize it. But yes. So today, as many of our customers know, our bottles and our vials are cylindrical in nature because they are injection molded. They don't have shoulders, which is what's typical for a traditional blown bottle or a blow molded bottle, a traditional packer bottle. That shape is not really attainable through injection molding. So we have done all of the due diligence required to see whether or not we could do it in a more traditional blown bottle format. And the fast answer is yes, we can. We've actually worked on that for a number of years, and it's a very interesting opportunity looking forward. It's a relatively capital-intensive execution, and so therefore the business opportunity would have to be somewhat substantial to justify the investment. But technically, we've done it. So the quick answer is yes.
Thank you. And what would be your package recommendation for DBB with probiotic?
I'm not familiar with DBB. So
Nor am I.
I'm going to toss that to Greg. Okay.
No, I'm punting it right back. I'm not sure what DBB refers to either.
All right. All right. And so,
Eric, we're going to let you answer that one.
Great. We're all in trouble then. So so I'll ask this. How does active polymer technology perform compared to a desiccated film?
Can you repeat that question?
How does active film, your active detect, perform as compared to a desiccated film?
I'm not sure. The active polymer is one of our we have many formulations, but one of our active polymers is a desiccant film.
Okay.
So If the question um, relates to desiccated foils, then I guess my answer would be that we would provide a tremendous amount more absorption capacity because we are not merely a surface coating. We can have a very thick layer of active polymer that enables us to get a tremendous reservoir of absorption capacity, whereas coated materials do not. I hope that answers the question. The way it was framed, I'm not sure I understood it.
That's fair. Fair enough. So this question, I'm going to be ad-libbing a little bit here. Multiple parts. What is the stability of probiotics in a capsule form? Initial cells to the end of the storage period, does it remain the same when it comes to its probiotic properties? I think that's for Greg.
Yeah, I can take a stab at that. And so to answer a broad question like that, it's hard to give a concise answer. I'll be as concise as I can, but you can make a room temperature stable probiotic capsule with proper choice of excipients, the probiotic material itself, the capsule material itself, the manufacturing environment of manufacturing the probiotic, but also of making the finished product, making sure you have, desiccated sweets in your manufacturing environment, and then finally choosing the right packaging material, which is what we've been speaking about today. So ask the question, what is the shelf life? It's so dependent on all of those factors. I can't give an answer, but I can say that you can make a room temperature stable probiotic capsule if you take proper care in choosing all of those various parameters that I just described.
And so within the 20 to 30 degrees Celsius range, which is more effective to control viability, the CSP technology or temperature control?
So CSP technology, or what was the last piece, Derek?
It's temperature control.
In my experience, that's a tough one. Clearly, elevated temperature isn't good for probiotic viability long term. I do know that you can heighten your chances of success if you've lowered your water activity. So temperature is always going to be the primary driver of stability. Lowering your water activity of your finished product material gives you a fighting chance at elevated temperatures. So in my experience, it would be temperature first, followed very closely by relative humidity. And they really go hand in hand. I mean, to do the best job and manufacture a product that has appreciable shelf life, you'd want to control your storage temperatures and mitigate and reduce your water activity to the lowest content possible.
And this, there's a request for some clarification on one of the slides early in the presentation regarding the cranberry data between the glass versus CSP. Was the cranberry dried, or what was the condition of the cranberry when it was used for that comparison data, if you know?
Yep. Yeah, the cranberry in that particular example is a dried and, as a matter of fact, a re-dried whole cranberry powder. So it comes in a relatively low water activity form. I would say between 0.1 and 0.15, which is relatively low for botanicals. And then that's admixed in with the other probiotic bacteria and the other excipients that might be used in the capsule manufacture. But to answer the question, the cranberry powder came in as a dried powder.
And in those studies, can you name what strain of probiotic was used?
In that particular example, it's a multi-strain combination of, I believe, 4 different probiotic strains.
And so, Billy, do you need custom automation? Do you need custom automation to set up a stick pack or blister pack samples with CSP film?
To set up samples, no. For commercialization, yes. But samples, we've worked with our customers to provide pre-cut samples that they could manually drop into a stick pack or into a blister or a sachet be it on their manufacturing lines, so they don't need to, invest in automation prior to having data to substantiate that investment. So yeah, no, we could work with them so that custom automation is not required for the sample stage, but typically it would be required for commercialization.
All right, thanks. And we have time for one or two more questions. If your question doesn't happen to get answered in the time for this current webinar, remember you can always click the email us button, and that'll set that question on over to us, and we can get Billy and Greg to answer all those questions for you. And so this next question is, can CSP provide us with any information about its active polymer technology that they can share with customers?
I'm not sure I understood the nature of the question, but I would say in general, yes, we're happy to share some information with our customers or prospective customers. I would suggest they can reach out to me directly at billy.abrams@aptar.com. I also believe, Derek, there's a mechanism by which the participants can get back into the webinar page and send emails to Packaging Strategies, and you'll disseminate those to Greg or myself. So in general, yes, we're happy to share information with our customers as we're able to. So it's just a function of communication and reaching out.
Absolutely, absolutely. And yes, this webinar will be archived on packagingstrategies.com. So at any time, if you want to review the information, you can also download the slides, but if you can always go back and review the presentation in its entirety with our speakers and their fantastic knowledge on the subject. And I'm looking to see, Philip, I believe your question was answered. How can I contact the speakers? Billy just gave his email address. And again, you can always click the email us button on the console, and that will send, just ask your question, and we will get that into the hands of our speakers. But it looks like that is all the questions we have at this time. So I'm going to close today's webinar, and I hope everybody will join me in thanking Billy Abrams and Dr. Gregory Layer for their presentation, as well as our sponsor Aptar for making all of this happen. And if you have any additional questions or comments, please don't hesitate to click the email us button on the console. And you can visit webinars.packagingstrategies.com for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you found this webinar to have been a valuable experience.